So now, the final question for the parameter now, we are going to derive that for the gravitational field. Now, constant. And then the gravitational constant, F, for gravitational constant. Now, when F equals to gravity constant, mass 1, mass 2 all over what? Over r squared. So from here we can figure out that you can do something like this. Go here, go. F r squared equals to what? G. M times m here, I can just put it what as m squared, for example, go here over m squared here over what? M squared. So this cancels out this. Here our G equals to what? Now we have F times R squared over what? Mass squared. Now G here, this is force. And force is in kilogram meter Pascal square. Times right R, distance of separation. Now we have meter, here half square. Then we have mass kilogram square. So now our G here equals now 1 kilogram here, cancel out 1 here. And meaning what? Meter times meter square here, we have meter cube. Yeah, 1 meter times 2 meter square here, we have meter cube. S to the power of minus 2 here. We still have another kilogram here. 1 kilogram cancel out 1 here. So now this becomes a G equals to what? This will come up here. We have kg power of minus 1 meter cube Pascal square. So now this is the unit for G. Then dimension here equals to what? Kg here. Kg here in this case is what? Is meter, is a capital M minus 1 meter L3 seconds here minus what? No, capital T, sorry, T here to the power minus 2. This is the dimension of the dimensional what? Constant. So now we all know that dimension can be used to describe or to find out the correctness of a what? Of a physical what? Quantity. Now, for example, now another application of dimension is to what? Is to verify the correctness of an equation. To verify the what? The correctness of a what? Of an equation. So now, for example, now, so the second application is to verify the correctness of a physical what? Equation. Now, for example, verify the correctness of what? Of physical equation. Physical what? Equation. Now, according to law of homogeneity, that what we have on the left must be what we have on the right. Now, for example, we have V equals to S, so V equals what? U plus what? AT. We should use this to verify whether this equation is correct or not correct. But remember that in this case, whatever is the left hand side must be equal to what we have in the right hand side. So now the SN of velocity here is what? Is meter per second. And please remember that a pure number does not have a dimension. Here is equivalent to what? This is initial velocity for meter per second here again, plus acceleration is a meter Pascal square times T here, which is what in second. Meter Pascal here is equivalent to what? Meter Pascal in this case plus here meter minus 2 here plus 1 go. Here you have meter per second equals to meter per second plus what? Meter per second. Minus 2 plus 1. Now, this means that here we have the dimension of this is L T minus 1. Again, L T minus 1 plus what? L T minus 1. You see? Now, what we have here is what we have here. Whatever is the right hand side is what we have. Now, for example, we have L T minus 1. When we add, we have 2LT minus 1. But remember that we are talking about the dimension. And remember that pure numbers does not have a dimension. You see, what we have here is what we have here. Dimension is what is correct. Then we say that this equation is dimensionally correct. So now, for example, let me look into another example. Now, we said S equals to what? UT plus what? AT square all over 2. Let us see whether it is correct or not. Go. Now, in this case, S is in meter. Go. This U is velocity times time, second go, plus here is a meter Pascal square times time here, second, but in square go over what? 2. Here we have meter here equals what? Meter here S minus 1. Here is like 1 go plus 1 plus here M S minus 2 here again plus 2 over 2 go. You have M equals here you have only 1 M go minus 1 0 plus here M S minus 2 plus 2 0 over 2 go. Now M here n to the power 0 is 1 go. M 0 again go. M again go over 2. Now we can remove these 2 because dimension. Now we have L here equals L plus L over 2, for example. Now we can remove this since dimension. What we have here is what we have here. Now you can say that L equals what? For example, here 2L go. If we can remove this 2 here, that's all. Again, dimension here is L equals L. Now remember that pure number does not have a dimension. Please. So this is how we use dimension to verify the correctness of a physical equation, please. So the last one, we are going to use dimension to form an exact relationship between measured physical quantities. The last one is what? Is derivation to derive the exact relation between physical quantities.